post it for later. Okay, so you guys can see what my papers. Okay, so you'll be able to go on to Google Classroom after, or if you haven't already, we're looking at outcome 9A now, which is going to get us into logarithmic functions. So the whole last section that we just did was on exponential functions and graphing it and doing transformations to it. Logarithmic functions, we're going to do exactly the same thing. We're going to talk about logarithms. What are they? Where do they come from? What does that look like? And then we're actually in the second part of the unit, just like we did in the last one, we're going to talk about graphing them and then transforming them, right? So shifting them, moving them, and flipping them, and doing all that fun and wonderful stuff that we've been doing all the way along. So to get us started, last unit, we looked at an exponential equation, right? We were able to look at an exponential equation of 9 to the power of 2x. Hey, Winnie.
Hi.
We're just going to start 9A. Okay. So when we start to look at, if we had these equations, 9 to the power of 2x is equal to 27 to the power of x to the plus 1, we basically, last unit, we were able to look at this and say, hey, if we got these to be same bases, then we could take our exponents and set them equal to each other and solve. So in this instance, we would have taken the 9 and we would have converted that to 3 squared to the power of 2 to the power of x. And then the 27, we could have rewrote that as 3 to the power of 3, all to the power of x plus 1. And then because then we had our bases the same, then we could focus on these exponents, because if our bases were the same, then our exponents were equal. And we would get, well, 2 times the 2x would have given us 4x. And we would have had on this side 3 times the x plus 1, which would have given us 3x plus 3. So then at that point, you would solve for x. You would gather your x's together. So I would subtract the 3x over and subtract the 3x over, and I would get x is equal to 3 in answer. So that's the beauty of when we have exponents and setting up an equation like this. As long as we can get bases that are the same, we can find out what that variable is. Now, that's all great, except for what happens when we have bases. So like in this case, I have 4 to the power of 2x is equal to 9 to the power of x plus 1. What if our bases, we can't get them to be the same? Like, there's no way around that. Then this is going to create a little bit more difficult of a scenario for us. We can't necessarily just use an exponential equation to do this. We need to use something else, which brings in the whole idea of logarithms. So this unit is basically going to take us a little bit further and give us the ability eventually to be able to solve equations like this without having to use them as exponents. We can convert them to a logarithm. But in order for us to convert them to a logarithm, we need to know what the relationship between an exponent and a logarithm is. Well, we know that we had an exponential equation is always made up with, you've got a base, you've got an exponent, and you've got what it actually equals, right? So in this instance, though, if I decided, so remember inverses from the very first unit that we worked on and finding the inverse of an equation? We were trying to find the inverse. We were really just taking our x and our y and we were swapping them, right? So if I wanted to take the inverse of our exponential equation that I have, then all I would be doing is literally swapping out my x and my y. So now what I've got is the inverse of an exponential function looks like so. That inverse, this inverse here is our logarithmic function. So simply put, any other ones we've been doing, taking the inverse of, we didn't actually, there was never a specific name or anything that attaches itself to it. But in this instance, when we're looking at an exponential function and we take the inverse of it, we actually create that logarithmic function. So that's going to be a critical piece moving forward, that basically an exponential function, when we take the inverse of it, becomes a logarithmic function, okay? One other thing to note in this is that our logarithmic function, okay, is simply the inverse of it like that, but it can also be written, and we will see it written like so, where you have y is equal to the log of c, so that base of c is of x, okay? So you've got, so think about this. This is what we've got going on here. So this is saying that your c goes in right here as your little base. Your value, your number that you get, is going to show up as x in here, and your y shows up on the other side of the equal sign. So these mean the same thing. So if I've got y is equal to log c of x, that equals the same thing as that. I just rewrote it so it was a little bit bigger so you'd see what was connected. So having said that, this is looking like kind of an exponential form of understanding, where this is looking at it in terms of a logarithmic form of understanding. So what we're going to do today is we're going to be working in both modes. We're going to work between both of these scenarios. Where we work in exponential, we should be able to take an exponential equation function that we have and convert it to a logarithmic equation. And we've got to be able to be comfortable with transferring back and forth, because as we work through some of these things, there's certain times when it's easier for us to use an exponential equation, and then there are other times where it's really important that we use the logarithmic equation. So we have to become very comfortable with converting between both logarithmic and exponential forms. Questions at this point? Okay, so here I have just a very kind of, there's so many different ways we can look at this in terms of like understanding the conversion process and kind of trying to remember, or ways to remember it. So when we look at a logarithm, okay, this is log, this is a little c in here, and then you've got your x and you've got it equal to y, okay? So when I want to convert a logarithm to an exponential form, whatever I have down here in my little, I always call this, is still considered my base. This c down here is still considered my base here, okay? The y over here, anything on the other side of my logarithm, that's always that's considered my exponent, right? And then this value, x, is always, it's just considered a number. It's the value, right? It's the value of what it equals. So if I wanted to take, let's say we had the log of, I'm going to say 6, I'm going to put a 36 in here, and I'm going to put a 2 here. So this is a logarithmic form of an equation. Log 36 equals 2. I want to convert it into an exponential form. So if I want to convert this, I have to think very carefully of what each of these values actually represent down here. Okay, so this being my base down there, that 6 represents my base. And in any of my y, or that value on the other side of the equal sign, this represents my exponent over there. And then this 36 represents my number, my value, right? The number or value. So if you can identify which each piece of that equation, what they represent, when you go to create the exponential form of it, okay, exponential form being the c to the power of y is equal to x, my c, that is my base. So in this instance, if I'm trying to put it into exponential form, my base is a 6. So I'm going to write my 6 down as my base. My exponent represents that little 2. So I'm saying 6 to the power of 2 equals, on the other side, in my exponential form, the x represents whatever that value is after your log. Well, this is my n. This is my number, my value. So now I've got an exponential form of the equation. And hey, take a look. After you get it wrote, it should make sense of what you've got. This is saying 6 squared is equal to 36. That makes sense, because 6 squared, 6 times 6, equals 36. So this does hold true, right? Like once you convert, if you convert from logarithm to exponential, you should be still left with an equation that actually is true, right? Because see, look if I did this differently. If I said, oh, well, this is my base, and I said 2 to the power of 6 equals 36. Does that hold true? 2 to the power of 6 is equal to 36? No, because 2 to the power of 6, that gives me 64. So that doesn't equal 36. So I know that isn't correct. So when you're doing this conversion, you should be able to see and know for a fact whether or not it's true or not, right? So it's just a way of checking to make sure. So your base is always that little number down here. Right after your log, there'll be a subscript number. And then over on the other side of the equal sign, that's where your exponent is always going to show up. And then the resulting answer of that base to that exponent will equal the value after log. Does that make sense? Is there any questions? That's a lot of kind of thrown at you. The biggest thing is just kind of keeping track of that conversion process. Okay, let's take a look.
Or is the thing you put the x over, it says 2 to the power of 6 equals 36. What's the numbers underneath? There's 36, and then what's the first one?
64. I just had a 64. Yeah.
64.
Yeah. Yeah. Okay, so if you are asked to evaluate, we can't exactly necessarily put this into our calculator nice and in neat fashion, but what we can do, whenever you're asked to evaluate a logarithm, always convert it to an exponential form. So I'm going to put in here, always convert to exponential. Okay, whenever you're asked to evaluate some log, you're going to always convert it to exponential form. So meaning I'm looking at log 232. Well, in theory, to create an equation out of this, I basically have this as it's got to equal something, right? I don't know what the something is. Now, for a lack of a better, I don't want to necessarily use a question mark, so I am going to use a label or a variable. And in this instance, I go back to my standard of just using an X. I don't want you to get mixed up with that just being an X showing up in these, right? Like this was just a standard. Quite honestly, I could have used any old variable in any of these spots in here, right? I've got my C as that represents my base. I've got an X and a Y. It doesn't, those are irrelevant. I can use whatever variable I want. So if I'm looking at this now, I've got a logarithm. I want to set this up in exponential form in order for me to evaluate it. So in this case, I have to think to myself, okay, if I'm setting it up in exponential form, I need to know what a base is, what my base for this particular question is. And I hope you're seeing that the 2 is your base. So I'm going to write a 2. And my exponent, which would represent the x, so I'm going to put my exponent of an x. That's going to equal this value here, which happens to be my number, right? Which equals 32. So this kind of starts to look like, I hope you're seeing, this is kind of what we were working with in the last unit, where we were given kind of an exponential equation, right? You've got 2 to the power of x equals 32. Some of you may look at that and go, oh, I know what x equals just by looking at it or recognizing it. If not, go back to kind of what we were doing right at the beginning of today, where I said, hey, you've got an exponential equation. You want to get bases to be the same. So you convert to get both your bases the same so you can set your exponents equal to each other. So in this instance then, if I've got a 2 to the power of x, well, that's not changing. I can't reduce that any. But can I reduce the 32? So if I think about 32, can I represent it differently? 2 to what power is going to give me 32?
5.
You betcha. So if I know that 2 to the power of 5 gives me 32, I got bases the same. So that only must mean that x equals 5 in this scenario. So that's really telling me that the log of 232 equals 5. Does that make sense?
Wait a minute. Where did you put the 5 on the final answer? Is it at the?
So I'm okay if you set it and you've left it just as x equals 5, because we knew x was basically my answer that I was trying to find, right? Or you can rewrite it back in and set your whole logarithm of 232 to equal 5. Either way, I'm okay with either one.
Oh.
If you just want to leave it like that, you're good.
I'm sorry, I just got a bit lost where so the 32 as the what was it called? Was it the number value? I thought
Yes.
The number value goes on the other side. So it would look like 2 with an exponent of 5 equals 32. But in this case, because it's not because we didn't know what 5 is, do we just write it as that?
But look at my number value. When I set up here's my exponential form, right?
Yep.
So my number value went over on that other side.
Okay. Is it all right if we write it in that way, or would you prefer the other one?
Like this?
Yeah.
You need to get it here first.
I mean, like if we write it as the final answer.
Oh, you're just saying if you left it like this, 2 to the power of 5 equals 32, like that?
Yeah. Does that count, or do you prefer like it log?
I would either, if you're going to do this, that's fine that you recognize it that way. But ultimately, we're asked to evaluate. I need to know what the log 2 of 32 is. Ultimately, I need to see 5 as my final answer, right?
Oh, okay.
That you've identified it as that. Yeah.
All right.
Okay.
Okay, that makes sense.
Okay. Okay, so let's try the next one. You've got log 749. So same thing. You've got to convert it to an exponential again. So I'm going to set it equal to x, because that's what I'm ultimately trying to figure out. I'm trying to figure out what that value is, what x is. So again, identify what your base is. So in this case, your base is 7. And my x over on this other side, that represents my exponent. And my number value that goes on the other side of the equal sign should be 49. And some of these you're going to get where it's just becomes, you're not even going to write some of this down. You're just going to recognize, oh, you're like my brain, I go 7 to what power is giving me 49, right? Like I'm already starting to talk into a different language of Oh, 7 to the power of, what do we know? What is x going to equal?
2.
You betcha. So right now, without having to change to the same basis, right, I can look at this and say and recognize 7 to the power of 2 is going to give me 49. If that doesn't come easily to you, then you can go ahead and switch your bases, right, and get them to be the same. If it doesn't stand out as easy as that, then you might want to change your bases and get them to be the same so that you can get your exponents, set them equal to each other, and solve for x. But if it's just like some of them are pretty straightforward, we look at them and go, oh, okay, I recognize that. That makes sense to me. So you're going to end up using a little mental math at times, okay? Any other questions? Okay. So let's move on to the next page. Where do I have us going next? Okay, so basically where we go next is we're going to use these logarithms a little bit more and kind of play around with them. Typically in our number system, we have a base 10 of powers of 10. Logarithms can be used in a base 10 as well. That's probably the most common, and on your calculators, you'll see you'll have a log button on your calculators. The log button on your calculator will be specific to a log 10 scenario, okay? So, but typically when we write a log, if we're saying it's as a base of 10 or it has a little 10 down here, we typically won't write it. We won't write the little 10 in there. We just recognize that if it's just a log and there's no little base or no little number down here, it means log with a base of 10 to it. Okay, so that's something we just have to take note moving forward, that we recognize that when we see a log with no little number down below, like in the base spot, then that means it's a log with a base of 10, okay? Now, on your calculator, you can just basically plug and play into your calculator, right? Like you go and plug log of 1 into your calculator, and you are going to have, and now every calculator is going to do something different, right? Sometimes your calculator might say you have to hit the log button first and then type the number 1. Some calculators will want you to type the 1 and then hit the log button. So there's different, right, depending on your calculator and what you got going on. I know my calculator that I've got here at home, I actually have to type in the 1 first and then hit the log value. And what are you getting for an answer?
Is it a decimal?
You shouldn't get a decimal. If you go 1 and I hit log or log of 1, you should be getting an answer of 0.
Oh, I got that. I just didn't think that was ready.
Oh, okay, there we go.
Okay, but think about this, you guys. So technically, if there is no number down here, we're thinking of it as a base 10, right? So if I converted this to an exponential form, I'd be saying I'd have 10 to some power, because technically we know the answer is this, but let's just play this out like we don't know that this is the answer. And then it would equal my value of 1. Well, 10 to what power equals 1? Well, knowing what we know from our calculator, any number to the power of 0 is always going to give us 1, right? So that's why when we look at this, that's why our log of 1 is actually coming out to 0. Okay? So think about the next one. What did you get? You get log 10. What do you get? Did you get 1 for the log of 10?
I did.
So think about it the same way, right? So if this is a base 10, well, this is basically saying 10 to what power is giving me an answer of 10. So 10 to what power? Well, the only way I can get a resulting 10 out of it to have the same base is if x equaled 1, right? So that's why, and that's where you're going to start to walk in kind of two different worlds here of the use of your calculator, but also transitioning and making sense of what does this actually mean? How could I calculate this mentally in my head? Or what does that process look like if I didn't have a calculator, right? So if I look at the log of 10,000, your calculator should tell you that it should be an answer of 4, right? So again, if I looked at this, I'd be saying 10 to what power gives me a resulting answer of 10,000. When I look at this, 10 to the power 4, which would mean 10 times 10 times 10 times 10, would give me 10,000 with a resulting answer. And then if I go 0.1 log, I'm getting -1 as an answer. Same thing, I'm going to say x to the power of, or 10 to the power of x equals 0.1. Now, decimals are a little funny because think about this in terms of a fraction. If I say this correctly with the proper notation, this is saying 1/10. So this is really the same as saying 1/10. Remember when this was like, this would be like 10/1 down here? But for me to move this 10 to the power of 1 up, that would actually make this a 10 to the power of -1, right? Hence, now, if I look at this and say, oh, x has to be a -1. That's why we're getting a resulting answer of -1. And then if you put into your calculator and you go 0.01 log, you're getting an answer of -2. So same thing, if you set this up as an exponential equation, I'd be looking for 10 to the power of x is equal to 0.01, or that's like saying 1/100th. And if I wanted to get same bases, that would be like saying 1/10 squared, which if I wanted it all up on the top, it would be saying 10 to the power of -2. That's why I'm getting the -2 for an answer. Questions?
That's just, you've been shredding it down.
Okay. Winnie, how are you doing? I think Winnie must be muted. So for those that are waiting, what you can do too is start looking at the next ones. These ones aren't with a base of 10 anymore. These have different bases to them, and it looks like some of these are just a base of 2. So your calculator, you're not going to use your calculator to do these. Now you're going to have to use a little bit of mental math and think about using that whole idea of converting to an exponential form, okay? So with log of 2, with log base 2 of 1, you're looking at this as saying, oh, it's a base of 2, so I want to know 2 to what power is going to give me 1. And what are we thinking?
Zero?
Yeah, that's exactly it. Because the only time I can get a 1 of a resulting answer with a power is if that power is 0, right? So 2 to the power of 0 is going to give me 1. Absolutely. So think about the next one. You've got 2 as a base here. To some power has got to give me 2 as a resulting answer. What is that exponent going to be in order for me to get a 2 as a resulting answer?
1.
You betcha. So the log of 2 is 1. So log of 2, base 2 of 4 is going to give me 2 to the power of something is got to give me 4 as a resulting answer. What's that going to be?
3. Wait, oh wait. No.
Yeah.
Would it be, it would be 2.
Yeah, you're
Yeah,
right.
there we
Because
go.
2 to the power of 2 gives me 4, right?
The next one should be 3 then. Yeah.
There you go.
They're basically
So
just
there
counting.
you're. Yep. 2 to the power. Well, no, we're not counting. Don't just assume that.
Okay.
You're all in order.
Yeah.
I want you to have some understanding there, Bruce. So really the next one is looking at 2 to what power gives me 8. Yeah, besides the counting that you're seeing the general pattern happening, we're looking at 2 to the power of 3 actually gives me 8. So 3 would be my answer of that log. And the next one, you're seeing that 2 to the power of x equals 16. So I want to know what power, 2 to what power will give me 16. You should see it come out as 4. Okay, now we're going to break your pattern, Cruz. No, that's not going to work for this one. So I'm going to say 2 to some power is got to equal 1/2. What's that going to equal?
-1.
Yeah, that's exactly it. So this right now is saying 1 over 2 to the power of a positive 1. But in reality, I can rewrite that 1/2 to show it as 2 to the power of -1. So this -1 is what my resulting answer is. You betcha. So then if I go 2 to what power is equal to 1/4, you're going to tell me it is?
-2.
Yep. And then 2 to some power is equal 1/8.
-3.
And that's going to equal -3. You betcha. Okay, so let's look at log of 1 million. So what's our base to this one?
10.
Yep, so we're basically looking at this as 10 to what power is equal to 1 million.
Would it be 6?
Yes, you betcha.
Is the exponent always going to be just the amount of zeros that are there?
In this instance, when we're dealing with a base 10 like this, absolutely. Yeah.
Okay.
Yeah. Yeah, because did you recognize that up here when
Yeah,
we did the
I was noticing that.
10,000? Yeah. And the 10 we had, right? And when it was a 1, there was no zeros. And then when we get into the decimals, that's when we start to pull in the negative values to it. Yeah.
Mhm.
Good catch. Good catch. Oh, the next one. That one looks fun. So we've got a base of 9 to the power of something has got to give me the 5th root of 81. Okay. Any ideas that we want to try with this one? I think my suggestion to you guys would be, let's get rid of this radical in this format with this 5th root. Can we change that to a fractional exponent? We did a little bit of that in the last unit, right? So really I would have this as 9 to the power of x. This would be 81 to the power of 1/5, right? That root is going to be what's in my denominator of my fractional exponent. Now, this is kind of setting itself up kind of like those exponential equations we did from last unit. This one is going to require us, we don't have same bases here happening on this case, and it's not easy for us to just look at this and recognize, oh, it's going to be this value for x to make this work. So this is a prime example of one that we will probably want to use our knowledge from the last unit on solving those exponential equations by getting those bases to be identical again, right? So in this case, we need to identify what is a base. What could we use as a base that would make both of these sides to be equal, to have the same bases?
Three?
Okay, we could totally use a 3. So that means the 9 is the equivalent of saying 3 squared to that power of x. And the 81 on this side is the equivalent of saying 3 to the power of 4 to the power of 1/5. Okay, so now I've got it where I've got same bases. I just have to clean up my exponents on both sides here, right? So in this notion then, I'm just going to move it over this way. I'm going to have 3 to the power of 2x is equal to 3. Now this is a 4 times a 1/5. This is like saying 4 over 1, right? I just want you to identify what is getting multiplied together, your numerators and your denominators, right? The 4 times the 1 times the 5. So this really becomes 4/5. So now what I end up doing is these exponents I can set equal to each other. And I can go ahead and solve for x, which means I'm going to take and divide both sides by 2. So when I take a fraction and I divide by a whole number, this whole number is like saying over 1, right? So for me to divide, I'm really going to take the reciprocal. I'm going to flip that 2 and that 1 around. And I'm going to end up multiplying. So I'm really multiplying by a half, which in that case, x is going to equal to 4 over 10, which then if I reduce that, that's going to reduce to 2/5. That one was a long question. Okay. Let's set up the next one. You've got log 3, 9 root 3. So my base is 3, don't know my exponent, that's what I'm trying to find out, and I've got 9 root 3. So in this one too, we've got some interesting things. We can't just necessarily look at this and recognize what x should be here. So 3 to some power is going to give me a resulting answer of 9 square root 3. So now my dilemma is I've got to basically, just like this last question, get my bases to be the same on either side of my equal sign. And then from there, then I can set those exponents equal to each other again. My problem is I got to determine what am I using for a same base and what do I have going on in here already. So I've got 3 to the power x on that left-hand side. It seems as simplified as I can do. So my goal now is if this is a base of 3, I need to get everything over here to be represented as a base of 3 as well. So right now I've got a 9 and I've got the square root of 3. That's the same as saying 3 to the power of, if it's a square root, this is to the same as saying 3 to the power of 1/2. So that got rid of the square root and brought that 3 to a kind of a whole number base. Problem is I got a 9 here. I need to address that too, because that's not as a base of 3 yet. So we need to fix that. So that 9, I could actually write that as 3 to the power of 2 times 3 to the power of half on that side. So I've got both of that 3 squared times the 3 to the power of a half. What do I do? What do you guys remember when you are multiplying same bases together? What do you do with your exponents?
You add them?
Yeah. So in this case, then, I really have 3 to the power of 2 plus 1 half. So if I look at that, I can take that whole number of a 1 again, or the whole number of 2 and put it over a 1. That would mean I would need to get common denominators. So my suggestion is get a common denominator of 2, which means I'm going to have to multiply top and bottom by 2, which is going to give me a lovely fraction that looks like 4 over 2. So 4 over 2 is the equivalent of just a 2, right? So that means I've got this as 5 over 2 if I add these fractions together, which now that I've got same bases, now I can go to my exponents, set them equal to each other. And in this instance, there's nothing, oh, I went off my page, sorry. There's nothing in here that we actually had to do any further calculations. We did all the calculations up front so that by the time we got same bases, we got our sides all simplified down to a single result. I end up with my actual answer of x should equal 5 halves. And your last one, you've got log of 6, 1. So you've got a base of 6. You don't know the exponent. And it's got to equal 1. So you should have a resulting answer of
0.
Mm-hmm. You betcha.
I'm just a bit confused with the last one.
Yep.
You were able to determine 9, the 9 in the brackets 3 with it being squared because it was a square root, or that whatever, I forget what it's called, but whatever it is over the 3.
In here, like
Yeah.
because this is a square root, that's why I got the 1/2.
Okay, that
Yeah.
that makes sense. That was
If this
just where I was
if this was
confused.
a little cube root in here, if there was a little 3 in the index, then where this 2 is would be a 3 instead.
Okay.
You know what I'm saying? Or if
Yeah.
this was a little 4 in here, then where this 2 is would be a 4 instead.
All right.
Okay. Okay. How are we feeling? Do we want to stop there? And like there's more to this first section, but I don't know that I want to throw more on your plate right now. What do you guys give me some feedback. What do you think?
It would be nice to have some time to look at this before other stuff.
Okay, that's what I'm feeling right now. I think you guys just need to have some time to kind of manipulate between both of those, right? Like to kind of transfer back and forth. Let me just get my notes and see what assignment. Maybe I can give you a few questions to work on, and then you're not looking at all of it, or at least then you can kind of pinpoint it to certain ones. Oh, and I don't have the practice questions here. Okay, you know what I'm going to do is when we go offline, then what I will do is pull up my notes and the assignment questions and just send you a text with the ones, like there might be a couple or something. I say, hey, do these questions only, okay? Out of assignment number 1, and kind of play around with those and try them. And then what we'll do is we'll just continue on. We'll just break this first lesson into 2 parts. So what we did today, and then what is today? Today's Tuesday. Okay, so Thursday then, we'll do the second half of this then. And then we'll worry about transformations next week. Does that work?
Yep.
Yep.
Okay. Okay. So if you guys don't have any questions, then, and please, like, holler at me right now if you've got something you want to ask or anything that's kind of glaring that you want to make some sense of before we leave.
I think I'll just message you sometime if I do need to figure it out. But right now I kind of just need to look over it to make sure I know if there's something I don't understand.
Yep. Okay, fair enough. Okay, so what I'm going to do is let you guys go, but I am going to go through your assignment, assignment number 1, and just pinpoint a few that you should try out of these ones, that just to keep you kind of, so that it's making more sense, so that you don't do the whole assignment in assignment 1 right now. Okay, and then I'll text you that information.
Okay.
Fair? Alrighty. Okay.
Thank you.
You're very welcome. Have yourselves a great day, and we'll see you Thursday.